Welcome to day 3 of Biostatistics III. Right, topics for today. We will look at how rates vary over time. We will just discuss the Cox model, which is possibly the most important time to event regression model. We'll compare Cox and Poisson regression, and we'll spend some time thinking about how to assess and model for the non-proportional hazards, and then we'll think also about the effect of that on modeling for time varying rate ratios. So hazards can take a number of different forms. This bathtub shape is typical for mortality rates. It could be that rates are increasing. Decreasing rates are quite common in cancer survival. We have very poor survival early on, and then you actually have moderately good survival later in the time since cancer diagnosis. You could also assume that the hazard is constant. So don't forget that time can take different values here. It could be time from cancer diagnosis, or it could be attained age, or it could be calendar period. I think we've covered most of that. If it is constant, then it'll follow an exponential distribution, which has one parameter, which is the hazard lambda. So, and this distribution is memoryless, where the expected survival time for any individual is actually independent of how long the individual has survived. So, shape for Poisson regression. If the log of the rate is equal to beta naught, which is the intercept term, plus beta 1 times x, where beta 1 is the coefficient for exposure x, then we have that we get this baseline and then a multiplicative effect for exposure. What we can do is that for the baseline, we could actually divide that up into being piecewise constant. So within time periods, we chop up time and then assume that you get a piecewise constant hazard within the time periods. Note that here, the first time period will be left out of the equation because we've got an intercept term. So, and then what we find if we fit for looking at, I think this is colon cancer, comparing distant metastases with other sorts, which will be localized and regional cancer, that the mortality rate here is much higher for the distant metastases compared with other. It's piecewise constant here for the 2 years, and then from 1 to 3, 2 to 3, 3 to 4. So if we assume that the survival times follow an exponential distribution, then we could just simply model the hazard as a function of one or more of the covariates. And then from that, we can obtain an estimate of the hazard ratio for the treatment groups compared to the control groups, while adjusting for other explanatory variables. However, the method actually makes a fairly strong assumption that the hazards are constant, and it's actually quite common. And if anything, it's more common that there will be changes in the hazards over time. So if we actually want to model for the changes over time, we have got several options. What we can do, we can split by time and then assume that the hazard is piecewise constant, and that's what we did on day 2. We could use a more flexible distribution, such as we could use Weibull regression or flexible parametric survival models, or we could use a non-parametric function for the baseline hazard, and that's where Cox regression. Carrying on further with the parametric models, what we could do is we could assume that the time to event follows one of a standard group of parametric models such as Weibull or log normal or Gompertz, and then we can fit something called an accelerated Phelan model. So if we have the time to event is t with covariates x, then the accelerated Phelan model assumes that the expected value of t, given that the covariates, is equal to some expected value for a baseline distribution times the exponential of minus beta x, where this baseline distribution t naught is true for when x is equal to 0. These models have a very nice interpretation where the exponential of the minus beta is interpreted as the change in the mean time per unit change in x. And as we will discuss on day 4, these models are also collapsible. So that means the estimated effect of an exposure does not change if we add or remove explanatory variables that are not confounders. If the parametric distribution is appropriate, then such models will also be more efficient. They'll have more narrow confidence intervals. An alternative parametric class is the flexible parametric survival models or generalized survival models, which includes both proportional hazards and proportional odds models. And again, we will actually discuss them further on day 4. The issue is that the parametric models may be sensitive to the choice of parametric distribution. And so then when we're using the parametric survival models, we need to pay special attention to testing whether the model is appropriate. Now, the beauty of the Cox model is it doesn't make any assumptions about the shape of the of the hazard function. Instead, the baseline hazard is allowed to vary freely. The Cox model directly only estimates hazard ratios relative to the baseline hazard. And since the baseline hazard is not estimated directly in the Cox model, it is said to be semi-parametric. Note that actually when we actually have fitted a Cox model, then we can then subsequently estimate the non-parametric baseline cumulative hazard function for when x is equal to 0, and then we can smooth that to estimate the hazard. But again, we have to do the smoother here. To introduce the use of the Cox model through an example, what we'll do is we'll consider patients diagnosed with colon carcinoma 1984 to 1995, and with potential follow-up to the end of 1995 with censoring after 10 years. And the outcome is cause-specific death, so it's death due to colon cancer. And the particular interest here is in the effect of clinical stage ACT diagnosis. So we want to compare distant metastases versus no distant metastases. And the question is, how might we specify a suitable statistic? Right, continuing the example, what we do now is we take the two sets of data, those with distant metastases and those with other, and then we smooth the hazard over the follow-up time. And what we find is that the distant metastases have got a very high rate early on here, and then it approaches the same rate as those with other stages. And as a reminder, don't overinterpret the smooth hazards, because there's sort of some design decisions and you can get some strange results. So I think broadly speaking, we want to look at the qualitative patterns here. Right, Cox's proportional hazards models. It's got a very nice form where the hazard at time t given covariates x is equal to some baseline hazard, which is a function just of time, times exponential of beta x. So it's multiplicative here. So, and you could have multiple covariates here. So you could have beta 1 times x1 plus beta 2 times x2 plus through to beta k plus xk. And in particular, we're assuming that the covariate effects are proportional. So it is a proportional hazards model. What's amazing is that the Cox model does not estimate the baseline hazard. So it could be that this baseline takes almost any form, but it does directly estimate the regression coefficients beta. So the intercept in the Cox model, which is the hazard for the individuals for all covariates at the reference levels. It's basically when x is equal to 0. That's assumed to be an arbitrary function of time, so it could take any shape, and that's often called the baseline hazard, and we call it lambda naught of t. As what we did for the Poisson model, we can say that the log of the hazard is equal to the log of the baseline plus beta x, and then the difference between two hazards is a constant beta. So if you've got a rate for given x, and then the rate given x is equal to 0, the difference between those is beta x. And thus the two survival curves, the two hazard curves, are assumed to be parallel on a log scale. However, when we do the smooth rates here on a log scale, what we find here again is we find a large separation, but then it's much closer here, and this is suggestive of so this is not from a fit. This is from smoothing the two curves separately using mu-has. And then this shows a strong suggestion of non-proportionality. To fit a Cox model for this example, we are using the colon data to create a new data frame called colon 2. When we're transforming this, distant is when stage is equal to distant, and they're dead if status is either death due to cancer or death due to other cause. So in this case, dead is due to any cause. And then we can do a Cox pH, specifying time using the serve function, the survival time in months for any cause of death as a function of whether they're distant or not from this data frame. And then from that fit, we get a summary. And then this shows us that for distant is equal to true compared with the distant is equal to false, we get a coefficient of 1.37. And the exponential of the coefficient is 3.95. So that is the hazard ratio, and that is the log of the hazard ratio. This is the standard error for the coefficient, and then if we do 1.96, so this value plus or minus 1.96 times this value, and then exponentiate, we get these confidence intervals here and here. So it means you've got you'll report this as a hazard ratio of 3.95 with 95% confidence interval of 3.80 and 4.11. What we see here is if we divide the coefficient by the standard error, we get a z value, and then we can get a p-value which shows that it's highly significant. So this shows that distant metastases have on average 4 times higher hazard than the other. It's highly significant and it's a fairly tight confidence interval. Now, from the fitted model, what we can do is using the Breslow estimator is we can actually get some approximate smooth hazards for the baseline and for the exposed group. But it actually might make more sense to see this on a log scale, because on a log scale, we get a constant distance between these two curves because it's a proportional hazards model. Now these curves, I think, are useful for suggesting what the lambda naught looks like, but actually they are just a smooth approximation for what the lambda naught actually is. Now, can we fit a similar model using Poisson regression? But what we do is we do a GLM for dead as the outcome with distant as a covariate, and then we do an offset for the log of the survival time. So we're doing rate modeling from the column 2 data set, and it's Poisson outcomes. And then what we find is we get an estimate here of 1.75, and that is comparable to the 1.337. So it's not the same. And the question is, why is the 1.75 not the same as the Cox? And the issue here is it assumes it's a constant rate over time. In some sense, because we've assumed it's constant over time, then we haven't controlled for time, whereas Cox does allow a fairly wild change in shape of the hazard, while this Poisson actually assumes it's constant. What we could have done instead is, as discussed on day 2, we could split the survival time. In this case, doing it annually, because we're taking the survival time divided by 12, keeping distant as a covariate, creating a new time band, sorry, a new variable called time band, and then we do the Poisson years as being t-stop minus t-start, which comes out of the surf split, and then we do a GLM, Poisson regression, same outcome, same covariates, now including the time band as a factor. So we're now adjusting for different bands of time with the log of the Poisson years as an offset. And then what we find is we get the 4.12 here, which is a lot closer to what we got here, which was 3.95. So we can do Poisson splitting more and more finely by time to get a very similar answer to Cox. And this is showing how it's piecewise constant between years. And the ratio between these is assumed to be constant over time. We could also fit a Cox adjusting for age at diagnosis as well. So we've now doing a Cox for survival time in years, for death due to, in this case, it's death due to cancer. For age greater than or equal to 75 or age less than 75. That will be the reference. So also adjusting for stages equal to distant using the I notation here, and we do a summary from that fit, and then we find out that after adjusting for age, the effect of distant is actually larger. So these are the betas, the beta hat, again, we've got, so this is 1.64 for those aged 75 plus compared with those aged under 75. So we see that cause-specific survival is poorer for those that are older. And then we see that there was a suggestion of some confounding between stage and age, because this is raised slightly. And both of these coefficients are highly significant. We could also do fits here by age. So those are less than 75, greater than 75, less than 75, and greater than or equal to 75. First two were for distant, and the second two were for non-distant. And these smooth hazards are again from the Breslow estimator. Right. Arguably, the Cox proportional hazards model is the most commonly applied model in medical time to events studies. Its amazing property is it doesn't make any assumption about the shape of the underlying hazards, but it does make the assumption that the hazards are proportional over follow-up time. Note that generally speaking, we particularly when we're looking at etiology or treatment effects, we're actually more interested in how the hazard varies as a function of the explanatory variables rather than the shape of the underlying hazard, or actually so it's actually more the relativities between groups. If you actually are interested in looking at more the absolute hazards, then Poisson may be better, but you can also recover estimates of survival and smoothed hazards from a COGS. So I think we've already discussed this. So you've got so in Poisson, what you have is that your rate or hazard has an intercept term, and that's assumed in this particular formulation to be constant. But actually, the issue here is that you actually want this value to vary. And so what we essentially do is Cox finds a way to move from Poisson to a value here where this log of the baseline is non-parametric. And you could also have multiple covariates, which we use a bold symbol here. So the regression model was first introduced in Cox in the early 1970s, and is frequently referred to as the Cox regression model, the Cox proportional hazards model, or simply the Cox model. We can estimate the betas using the method of maximum partial likelihood. So what we find is that if a particular regression coefficient, say beta j, is not different from 0, then we say that the corresponding explanatory variable xj is not associated with the hazard rate of the response of interest. And in that case, what we may actually wish to omit xj from any final model. We should at some point discuss sort of that the modeling approaches. I strongly prefer that the modeling is pre-specified, unless you're wanting to do prediction. So if you're trying to do prediction, then you can start to sort of see which variables go in or out. But if you're wanting to look at etiology, I think it's much better to pre-specify which covariates you believe should be adjusted for. So now to check to see whether the beta hat j's are equal to 0. We can do that with a Wald test or a likelihood ratio test. So this can basically be from the Wald test you can take from a given fit. Well, if you actually compare two models with and without the covariate, then you can do the likelihood ratio test. We've already discussed that there's a close interrelationship between the hazard function and the function. For Cox, what we have is survival time t given the covariates x is equal to exponential of minus and then this integration from 0 to t, and then plugging in the definition for the hazard. We've got the baseline here and then this term here. But this term here does not actually depend on time, so then that can go out the front. And then this value here can now be interpreted as the cumulative hazard function. And then because this is an exponential, this can go out to be a power here. And then so we have is exponential of minus integral of the hazard to this power, and then we can recognize that that is equal to the swell function for those that were unexposed. So there's a nice relationship here. Survival is equal to baseline survival raised to the hazard ratio. This is particularly useful for doing prediction, and it shows that sort of like moving from proportional hazards moves to survival to a power. Now, we should be very careful here. The assumption of proportional hazards is a strong assumption, and that should be tested. Most software packages will provide estimates of survival based on the fitted proportional hazards model for any specified values of the explanatory variables, and we've provided a function to support that for plotting the hazard function. Don't forget that the estimated coefficients beta are log hazard ratios. To get the right ratios, we need to exponentiate the coefficients, and the confidence intervals for beta are on the log scale. Therefore, the confidence intervals won't be symmetric around the rate or hazard ratios. Okay, so going back, what we have is that the rate given time t and covariates is equal to some baseline times this set of this exponential of a linear predictor, and then on the log scale we get the log of the baseline plus the sum. And this is actually very similar to what we've used for Poisson regression and multiple linear regression. So what's important is that the intercept term here has changed to being a non-parametric term here. So we've got this set up here, and then what we can say is that the beta x is equal to the log of the hazard given covariates minus the log of the baseline, which is equal to log of this ratio. And so then what you've got is that this ratio is equal to the exponential of this. So the parameter beta hat is a log relative rate, and exponential of beta is the relative rate of the response. If you conclude that the data provide a reasonable evidence to contradict the hypothesis that X is unrelated to response, then exponential beta hat is a point estimate of the rate at which the response occurs in group for x is equal to 1 relative to the rate in which the response occurs in the same group for x is equal to 0. Or it could be x is equal to x plus 1 compared with x is equal to x for a unit increase in x. So confidence intervals are pretty much as you would expect. And then we exponentiate to get them. Most of this, I think, should be fairly standard for regression setting. If xj is continuous, then beta exponential beta hat the hat of beta j is the hazard ratio associated with a 1 unit change in xj. So time for some examples. So what we're going to do is we're going to fit a proportional hazard model to study the effect of sex, age in 4 categories, and calendar period in 2 categories on cause specific survival. So we're only looking at deaths due to colon cancer, and we'll begin by restricting the data to localized cases. Okay, so what we do is we're doing Cox using the colon data frame, and then we're going to subset here for localized. Survival is expressed in months divided by 12, so that'll be years. For status is equal to cause due to cancer, so it's cause specific, and we're adjusting for sex, age group, and year 85 to 94. And then from that fit object, we do a summary. And we find here, these are the coefficients, these are the hazard ratios, these are the confidence intervals, and these are the p-values. What we see is that this is close to but not quite significant between males and females, suggesting that the females have got a very slightly lower hazard ratio, but that doesn't quite reach 5%, but it's close. There's no difference, so the reference age group is less than 45 years there, and that shows there's no significant difference between under 45s and the 45 to 59s, 2% between the 60 to 74s and the under 45s, and a very strong difference in the oldest age group, and we find that that's more than 2 times higher hazard in the oldest age group compared with the youngest. So with that confidence interval here. And then after adjusting for sex and age group and calendar time, and then time since diagnosis, because this is not, time since diagnosis is done non-parametrically, we find that the more recent, actually this is odd because this would be actually, I think it's 75 to 84 is the reference. No, it's not odd. It's lower here. So that means the later calendar period, after adjusting for these other covariates and the primary time scale, has got a reduced hazard by about 25%, where the fairly tight confidence interval. I think we've discussed most of this already. The default method for painting ties is the Efron. If you do this in Stata or SAS, the default is actually due to Breslow. So you might find very slightly different point estimates if you've got many ties. So the test statistic here is basically sort of saying, given those covariates, do those covariates contribute whatsoever to the model fit? And the null hypothesis is that they're all equal to 0. There's very limited support for that. So what we find is that these coefficients are contributing in some way, which, given these strong p-values, is not surprising. So factor variable 6 was coded male as reference and female, and then we've got that showing here, but that's not significant. I think we've already discussed that. I think we've talked about that. Yeah, we've talked about that. Okay, so these significant tests test the pairwise differences, and they don't tell us much about the overall association between age and survival. To do that, we need to do a more general test. So what we can do is we can use the CAR package, which provides the linear hypothesis function. What this does is it says, given this fit, test whether these parameters are all equal to 0. So, and then the output shows that it's doing a linear hypothesis test. These are the hypotheses. What we find is you've got 3 degrees of freedom, a large chi-squared, and then an overall p-value. And it shows fairly convincingly that there's strong evidence that one or more of these coefficients is not equal to 0. There, I think we've already covered that. We can also do this using a likelihood ratio test. So what we do is we do a fit where we do not adjust for age group. Otherwise, the rest of this code is the same. And then we do an ANOVA to compare the original fit with age group to the second fit without age group, and then do a chi-squared test, and we find that we get this chi-squared, 3 degrees of freedom, which I think is actually the same fit values. It's not quite identical. 175 compared with 176. So I think this test is done using a Wald test. I think this test is a likelihood ratio, and that's actually a bit better fit. Yeah, that's here. We might also choose to model age as being a continuous variable. So what we've got is we've got sex and calendar period, but then we're treating age as being continuous here, and then we get a beta and a hazard ratio. And as a reminder, this is the hazard ratio for a unit increase in age. So for every year that an individual is older, on average, there'll be a 3% increase. Don't forget, if this was done for over 10 years, then we do is we'd raise that to the power of 10. So again, this is adjusted for sex and adjusted for calendar period. The main challenge here is that we're actually assuming that this 3% will be true across all ages. So it's there. Now let's take a bit of a sort of step back and say, right, so now we've done Poisson, then we did Cox. How are they different? How are they similar? So the two methods are very similar, where they both got log hazard or log rate is equal to some linear predictor. In both cases, the beta hats are interpreted as log rate ratios or log hazard ratios, they're both multiplicative. So that means if you get a rate ratio for males if you got a main effects model with a rate ratio of 3 for sex and a rate ratio of 4 for smoking, then the rate ratio for male smokers to female smokers is assumed to be multiplicative if there are no interaction terms. The biggest difference between the two is that in Poisson regression, follow-up time is classified into bands, and a separate rate parameter is estimated for each band, or smoothed. So what we could do is we could do it in bins and then put a spline smoother, say, through the bins, and thereby allowing for the possibility for the rates to change with time. But what it does assume is that the rate is constant within each band or each midpoint if you're smoothing. So if the rate changes rapidly with time, we may have to choose very narrow bands. In contrast, in Cox, we essentially choose bands of infinitesimal small width. Each band is so narrow that it includes only a single event unless we have ties. But we, unlike in Poisson, we don't directly estimate the baseline rates within each time band. Instead, we estimate the relative rates or the hazard ratio for the different levels of the covariates. So if you want to actually estimate the effect of time, particularly if you've got multiple effects of time, then Poisson regression is actually a more natural choice. So time by covariate interactions for non-proportional hazards and multiple timescales are in practice easier to model in the framework of Poisson regression, but we will also talk about this for Cox. So you could view the Cox model as the life table sort of ad absurdum by we're splitting time as finely as possible. So we're modeling one time covariate, in this case, so one covariate, in this case, the time scale, we're given one parameter per observed value of time, but then you profile out those time parameters by maximizing the, I don't think it's profile, it should be partial likelihood. And then we can subsequently recover the effect of the timescales by smoothing an effect of the parameters, but we've actually profiled it out. Okay, this is a bunch of code which is actually not especially interesting. The main point is that we're trying to sort of compare Cox model and Poisson. So that what we first do is we do yearly splits. So we split by those years, and then we aggregate, and then we collapse, and then we do a GLM. And then what we do instead is we do split by all of the event times, and then we do much the same thing. So we've got the cuts, ignore the last one, and then we do splits, group, summarize, then we do a GLM, and then we compare that with Cox, which is they're all using the same covariates. The only difference between these three fits, fit 2 and fit 3, is this is yearly, this is fine, and then this is Cox, and then we show the coefficients. And then we find here that the effects for all of these values end up looking very, very similar, much more between Cox and the fine Poisson. So we essentially get increasingly close values. So close, close, close here. So choice of timescale in a Cox model. In Cox regression, the hazard ratio typically compares the hazard rates of two groups at each time t. It's also assumed to be proportional for any of the given times. So since the comparison is made at each time t, the hazard ratio is automatically adjusted for the underlying timescale. For example, if we use attained age as the underlying timescale, then all of the hazard ratios will be also adjusted for attained age in the Cox model. If age is chosen as the underlying timescale, the effective age cannot be directly estimated since it's incorporated in the shape of the non-parametric baseline hazard. The adjustment of the underlying timescale is very efficient in a Cox model. It's adjusted for time in very small intervals. So if you have, say, one of three possible timescales, such as time and study, or attained age, or calendar time, the one of those which is the strongest confounder of the exposure outcome association should be preferred as the timescale of interest. For example, consider a cohort study when individuals are randomly selected from the population and then followed for cancer incidence. For most cancers, age is a strong confounder. If we're not interested in estimating the effective age directly, an efficient approach is to adjust for age as the underlying timescale, and there's a number of references here. Thibault and Benachou recommending using age as the timescale for cohort studies for cancer outcomes. And then they conclude, we strongly recommend not using time on study as the timescale for analyzing epidemiologic cohort data where entry has no clinical or biological relevance. To show an example, using attained age as the timescale, we go back to using the diet data set. We've got a scale being the average number of days per year. So we do a Cox, defining the survival time as being the date of entry minus the date of birth, and then scale to give it in years, and the date of exit minus the date of birth, and then divided by scale. So this gives age at exit and age at entry for the CHD outcome, adjusting for high energy from the diet data, and then that fit object. If we do the summary, then we get this output. And so what we find is that after a very, very fine adjustment for age, we get this age-adjusted hazard ratio for having a high versus a low energy diet with this confidence interval, and the p-value is just below 5%. So this is a test of equality of the coronary heart disease mortality rates between individuals with high and low energy intake adjusted for attained age. And we have assumed proportional hazards with respect to attained age. And this is a very similar test to the one that we've performed previously using Poisson regression and to the log-rank test. The effect estimates in p-values for the test and the effect of high energy are very similar in both the Cox and the Poisson regression models. A slight difference is that attained age was categorized in the Poisson regression, and the rate was assumed to be constant within each category. Okay, so how far have we got? We have introduced the Cox model. We've talked about the Cox model as being an alternative to Poisson. we've noticed that the baseline hazard is non-parametric. It assumes proportional hazards. Now we need to discuss how to assess the appropriateness of the proportional hazards assumption. Exciting stuff. Okay, this is a strong assumption, and its appropriateness should generally be assessed. When comparing an aggressive therapy versus a conservative therapy, it's not unusual that the patients receiving the aggressive therapy do worse earlier, but then have a lower hazard that is better survival than those receiving the conservative therapy further out in time. In this sort of situation, the ratio of the hazard functions will not be constant over time, as it is assumed by the proportional hazards model. And in practice, we actually find that there's many examples when the proportional hazards assumption is not observed and is actually, we would expect that it would not be observed. So we've already seen some previous examples of non-proportional hazards, although it's actually difficult, particularly looking at survival curves to see whether there is non-proportionality in the hazards, unless they're sort of crossing hazard curves. So if the hazard functions cross, it is possible that the effective treatment will not be statistically significant, despite the presence of a clinically interesting effect. As such, it is important to plot survival curves before fitting the model and to assess the appropriateness of the proportional hazards assumption after, I think we've repeated this, after the model has been fitted. Ooh, yeah, okay. Note that the hazard functions do not have to cross for the proportional hazard assumption to be violated. For example, what you could have is a hazard ratio of 4 that gradually decreases with time to a value of 1.5. So Hess gives a review of some methods, and Tourneau and Gramsch give a more up-to-date review. So there's a number of different approaches that one could use. One of the approaches is that you plot the cumulative survival curves and check that they do not cross, but that approach is not recommended. You could also plot the log cumulative hazard functions over time and check for parallelism, but that doesn't actually provide any formal fit criteria, and is more descriptive. I think that is described in the worked examples, but we're going to focus on 3 and 4, which are looking at for time by covariate interaction terms. So we're actually going to be explicitly modeling for the non-proportionality, or doing a plot of the Schoenfeld residuals against time to identify patterns. So we'll focus on the third and the fourth. So non-proportional hazards is really just a fancy specific name for effect modification by time on the log scale. And given that we've already been talking about effect modification, we can see that we just need to include some interaction terms and then use those terms to estimate how the effect of the exposure varies by time. As a reminder, Poisson regression also assumes proportional hazards, and that Poisson regression allows for non-proportional hazards by fitting covariate time interactions. So one of the challenges with the Cox model is that because we don't explicitly estimate the effective time, it's not so obvious how to fit for a time by covariate interaction. Okay, 2 approaches. We can explicitly split by time, or we can use some sort of special frameworks for doing time varying effects. So what we are actually interested in is the situation where the effect of a covariate varies by time. But that's not the same as thinking about the value of a covariate varying with time. And we'll discuss this distinction more on slide 73. We do not explicitly estimate the effects of the underlying timescale in a Cox model, but we can estimate interactions with that timescale. Note that it is possible to estimate the underlying timescale after fitting a Cox model using the base has function in the survival package and the Cox pH has function in the Biostatistics III package. We still allow the baseline hazard to vary freely, but relax the assumption that the hazards must be proportional over time. One way to model for the interactions is to split time, which is much what we did for Poisson regression. So we come back to using the surf split function in the survival package. And then that allows us to model an interaction with time. And we'll show an example now using the colon data to allow for different hazard ratios for the 2 years before and after diagnosis. And we've already seen that for this example that survival depends on the calendar period of diagnosis. I think we've got a hazard ratio of 0.72 for recent or versus early period. So would we expect mortality in the recent period to be 28% lower in all of the follow-up time, or is it conceivable that the effect is greater? These are the recent and early calendar periods, which was 85 to 94 versus 75 to 84. So if the effect is different early in the follow-up compared to later in follow-up, then we have a case of non-proportional hazards. And in that sense, the effect of calendar period would be modified by time since diagnosis. And then based on clinical knowledge, we choose to estimate the effect separately for the first 24 months of follow-up. So what we do is we take the colon data and then we subset for stages equal to localized, and we're going to split it based on survival time in months for cause-specific death, keeping data on age group, sex, and calendar year of diagnosis, and then we cut at 24 months and a long way out, and then we have a new variable called time band. And then what we can do is we make time band into a factor. Now we can fit a model containing the interactions between year of diagnosis here and time band. So we do Cox, and then we've got serve split data. So it's actually this T start and serve underscore mm, and that's the event from the split data for age group, sex, calendar period, and time band interaction. So we get main effects and an interaction. Now what's interesting is that the main effect for time band is not significant, it's not estimated, because we've already adjusted for the underlying time scale. So this is actually okay. So we've got main effects for age, for sex, calendar period of diagnosis, and then this sort of shows the how this is the interaction for later calendar period with the second time band. this is the effect. This is the main effect for the first calendar period, and then this is that's the second calendar period for the reference time band, which is the first, and then this is the change. And this shows that for the first calendar period, it's it's negative, so it's actually the hazard ratio will be substantially less than 1. It's and highly significant for the first calendar period, and the sum of those is going to be much closer to 1, and the interaction is significant. So that's the description of the data. We've already discussed that time band 2 doesn't have its usual interpretation because we've already adjusted for time band, and then we can estimate the hazard ratio for the effective calendar period. So it's 0.72 when we assume proportional hazards. For the first 2 years, it's 0.66, which is exponential of this. And then for the later, it's 0.655 times 1.38, which is the exponential of this. So, which is 0.9. We say that there is evidence that the effect of period of diagnosis is more pronounced in the earlier calendar period than the later. So, if the interaction effect was 0, then there would have been no effect modification and no evidence for proportional hazards between those two factors, between time and period. But we do see that the interaction effect is statistically significant. So now the next step is what we could do is we could reparameterize the model to estimate the effective period within each time band. So then instead what we do is we do later and time band with no main effect for time band and no main effect for later. So then we get that's the log hazard ratio for the first calendar period, and that's the log hazard ratio for the second, and we see that is not significant. The other values here will be unchanged. Note that we could also have used the lincom command rather than reparameterizing the model. I think what we did here is we made these into 1, 0, so we didn't have problems with the factor encoding, because I think that this will be a factor, but this is not. So that's 0, 1, and then that's a factor. So the again, the estimated hazard ratio for the later calendar period for the first 2 years is 0.655, and for the after the first 2 years it's 0.905. If to test if this interaction is statistically significant, we could do either a Wald test or a likelihood ratio test. So here what we do is we've got age group, sex, and the interaction, and then from that fit, we do an ANOVA for chi-squared. And importantly, the terms here are added sequentially. So you basically sort of saying, first you got null, then age group and sex and calendar period, time band, which there's no degrees of freedom, and then you've got the 1 degree of freedom for the interaction, which is the value there. So the previous Z statistic that we had was 3.27. Don't forget that if you square so basically a Z squared distribution has a chi-squared with 1 degree of freedom distribution. So both of these tests are testing the hypothesis that the interaction effect is 0 versus it being non-zero. And there are some small differences here because we're doing one using a likelihood ratio and one using a world, and the likelihood ratio makes sort of weaker assumptions and is better. Okay, so what do we got? We've got so hazard at time t given covariates under standard proportional hazards is a baseline times, and actually we could make this plus beta 2 x2 plus dot 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 plus beta k xk. There. So the hazard ratio for the exposed to the unexposed is given by exponential beta 1. That's assuming proportional hazards. And what we could do is now construct a second variable x2, which is equal to x1 times t, and include that in the model. So then what we have is that beta that the hazard is equal to the baseline times, and then the hazard ratio is you got basically a beta 1 from when t is equal to 0, and then like a change in the hazard ratio for a unit change in t for a unit change in x. So based on this, the hazard ratio for exposed to unexposed, or a unit change in x1, is equal to exponential beta 1 plus beta 2 times t, which is quite cool because it means now we've got that the hazard ratio depends on time. So an estimate for beta 2 being significantly different from 0 indicates that the hazard ratio is non-constant over time. If it's greater than 0, then it shows that the hazard ratio is increasing with time, and if beta 2 is less than 0, it indicates that the hazard ratio is decreasing with time. Note that's not a general test for non-proportional hazards. It just tests against the alternative that the hazard ratio changes monotonically and linearly with time. Another alternative might be that the hazard ratio is constant for an initial period, say up to 2 years, and then it takes a different constant. To test against this alternative, then we could construct x2, which takes the value 1 if the exposure is present, and t is greater than or equal to 2 years, or 0. And the resulting model contains both x1 and x2. Then the first, it should be 2 here, I think, is the first kind of period is that, and the second is the exponential of the sum of these. I think we'll show some code here. No, not yet. First of all, we're going to talk about time varying covariates. Now, we've been considering the situation where the exposure value is constant, but the exposure effect varies across time. But it's also possible that for the underlying values of the covariates could change during follow-up. For example, blood pressure, occupational exposures to carcinogen, parity, CD4 count, or cumulative exposure to cigarettes. Another application is in observational studies where an intervention may occur at any point in the follow-up time. At the time of the intervention, the explanatory variable associated with the intervention changes from sort of turned off or 0 or false to being turned on or 1 or true. And then for such data, we highly recommend the time splitting approach for modeling such data. That is, we split to obtain a separate observation at every value of the time varying covariate. The challenge here is that it only makes sense if there's discrete changes in the covariates. So if you've got a continuously changing exposure, this approach would mean you'd have to probably sort of split time very, very finely. Well, if you're sort of moving from like one state to another, then the time splitting makes much more sense. Exercise 22 is a really nice exercise looking at marital bereavement, where you're following before the loss of a spouse and then after the loss of a spouse. And there's a quite intriguing finding that actually the women seem to have better survival after their spouse has died. Bereavement in this particular case is a time-varying exposure where not all subjects enter, so all subjects enter as not bereaved, and some may become bereaved at some point during the follow-up. For these sorts of data, a distinction should be made between an internal variable, which relates to an individual and can only be measured while a patient is alive, and external variables which do not necessarily require survival of the patient for their existence. And I should sort of a broad point that care should be taken when modeling for time-dependent covariates, particularly with internal variables. And I think the challenge here is that the outcomes may be related and may actually change the internal variables. So you have your internal variable may change because you've got worse prognosis, and then that's predicting that will be associated with actually having an outcome, even if the internal has no direct effect on the outcome. So going back to the time varying effects, what we can do is we can use the TT function, and what we show here is the TT function is we define an anonymous function with a covariate x and time t with other factors. This is the prototype, and then this little function is defined as being equal to the exposure value times t is greater than or equal to 24. So if t is less than 24, this will always return 0. If t is greater than and equal to 24, this will always return x. So then what we find here is adjusting for age and sex, then you've got a main effect for calendar period and a time varying effect here. This is the 0.655 that we had before, and then this is the interaction hazard ratio for time that we estimated previously. So instead of time splitting, we could actually have done this using the TT function. And then the covariate in this case is later, which is a 1-0 variable. So in Cox PH, for the model formulation, you include a TT and then the variable of interest, and then you need to define the TT function here. So that's basically, you've got a hazard ratio. Oh, this is going to be difficult to do well. And then you've got here, and then here. And then this is 0.66, and then this is 0.66 times 1.38, which is approximately equal to 0.90. The cutoff at 24 months was chosen somewhat arbitrarily, although we sort of said it was based on clinical knowledge. For the first 6 months of follow-up, the estimated hazard ratio was 0.724, and then for the first year it was 676, and for the first 2 years it was 0.657. Choosing the cutoff after inspection of the data, important point here. Sorry, let me emphasize this. Choosing the cut point after inspecting the data will tend to invalidate the statistical inference, in that you're going to tend to sort of like report values that are too low. You should think about the study design before you do the analysis, the study design and the analysis plan before you do the analysis. So we have to examine only one possible alternative so we've only examined the one possible alternative to proportional hazards, which is a step function. In practice, it is possible to fit any model of the form. You've got a baseline effect and then an interaction effect, where these this f of t could have a number of different forms. Right, that was the first approach. The second approach is doing an analysis based on Schoenfeld residuals. If the proportional hazards assumption holds, then the scaled Schoenfeld residuals, which are diagnostic specific to the Cox model, should be independent of time. In its simplest form, when there are no ties, the unscaled Schoenfeld residuals have this form, where you've got basically the observed covariate and then a weighted set of covariates in the risk sets, where if you've got when you're doing a cohort study, the RJs are those individuals who are still at risk of having an event when the Jth event takes place. So now these Schoenfeld residuals are scaled, so they'll have a slightly different form. Okay, for our application to localized colon cancer, what we have is we initially fit a Cox pH for survival time, for cause specific mortality adjusting for sex, age group, and calendar period of diagnosis, restricted to localized cancer. This is just a bit of code so we get nice printout at the next line. So what we do is from the fit, we do a cox.z pH, and then we look initially at the chi-squared statistic and the p-value for the global, and that says that there is strong evidence that there is one or more time-dependent hazard ratios, where p is small. And then we look at the p-values and we find that no evidence for time-varying hazards for sex or for 45 to 59 compared with less than 45, or for age group 60 to 74. However, there is some evidence for time-varying hazard ratios for age 75 plus compared with less than 45, and there's strong evidence for time-varying hazard ratio for the later calendar period. Now, for these two here, what we find is that is negative, which is the correlation between the residuals and time, and then that is a positive correlation for the later calendar period in time. Now, the interpretation here is that as you get, for the older age group, there tends to be a decrease in the a decreasing slope for the log hazard ratio, and then for the later calendar period, strangely enough, it says overall there's an increasing slope, which is a bit surprising. Okay. So rather than just fitting a straight line to the residuals and testing for a zero slope, as we did for cox.zph, we can also do a plot of the residuals along with a smoother to look to see how the mean residual varies as a function of time. And then that smoother can actually give us suggestions as far as what the log hazard ratio is as a function of time. So we do the fit for Cox pH, and then we do a plot for cox.zph, and then a log transformation of time. So that means this is using, these are log effects here. And then what we do is we see that this is for the later calendar period. Now, this actually has got more of a quadratic pattern, where it looks like it might be decreasing here and then increasing here. So, but it does actually suggest that the hazard ratio will get closer to 1 as you go further along. So, well, if we look at this for sex of females, we actually, there's basically, that's fairly close to being a flat line here. So, what about a model including stage? So what we do is we drop. So this is a function which drops. So stage has got several levels, and we're going to actually drop unknown from this. So now we only get regional and distant compared with localized. I think there's very few there. And then we do a Cox pH on survival time, cause specific death for those with known stage, and then adjusting for sex, age group, stage. Now that's new, and calendar period of diagnosis. And then what we find is that compared with localized, there's a 2.31 times the hazard for localized, for regional compared with localized, and 8.3 for distant compared with localized, and that's highly significant. And then if we do a cox.zph, I think log is a reasonable approach for these data, because there's like it's sort of the rates decrease quite sharply. Then we find out here that moderate evidence for a change for regional, but very strong evidence for a change for distant, and it shows that it decreases. So it starts off being large, and then the log hazard ratio decreases. And again, the global is highly significant. And this is not surprising, because if we actually look at the the smoothed hazard rates, we find that distant is very, very high here. Regional is intermediate, and they all look much the same here. So there's sort of strong evidence for time varying hazard ratios by stage. And then we can use the Cox pH.has function to do a smoother for the hazard. So we've actually done a Cox pH, adjusting for stage, and then we can actually plot the hazards, and these are these will be proportional. But I think the point here is that because this is assuming proportional hazards, then there's proportionality which is enforced on these data. So that suggests that there's actually differences here. Well, if we go back, there's no differences here. If we do Cox pH with log equals y, then the hazards are plotted on a log scale, and we see that the predicted hazards from the Cox has the same distance all the way across here and here. if we actually do a plot for stage distance, what we find is we find that there's again, we've got an increase here, it's flat here, and then you've got a strong decrease here. And it's actually very few data here, but it sort of shows sort of like possibly it's actually you've got an increasing hazard ratio early and then a very, very strong decrease. And don't forget this is done with log time. So you definitely see this strong decrease over time. But a change of pace now. One of the other approaches we can take to deal with non-proportionality is actually have separate baselines for different strata. So the base Cox model assumes that the baseline hazard is an arbitrary function of time. And then that the hazard function for each of the groups are assumed to be proportional to that baseline. What we can do is we can relax this assumption and allow for separate baseline hazards for different groups, say for each level of age at diagnosis. And then this is known as a stratified proportional hazards model. So the stratification is not that you're doing it in separate groups, so far as you're assuming that the baseline is stratified, but then you're still sharing the other parameters. So, and it's particularly useful for modeling data where you've got non-proportional hazards are suspected for a particular factor, but it's not of primary interest. So a model stratified on age group is analogous to including age group and time interaction in a Poisson regression model. So, well, and it's straightforward to sort of specify this in Cox pH, and you can just use the strata term in the Cox pH formula. And hopefully we'll have an example of this. Good. Okay, so we've got Cox pH, and the only real change here is that instead of adjusting for age group as a main effect, or trying to do a sort of interaction or splitting, what we do is we sort of say plus strata age group, and then we no longer get effects here because this basically means we get different baselines for each of the 4 age groups. And then, but this is really, really nice because now it's sort of saying after very finely taking care of the baseline hazards for the different age groups, all of that's taken care of. What is the average hazard ratio for sex, adjusted for time scales, adjusted for age groups, and adjusted for calendar period of diagnosis, and then we get this estimate here with a very small p-value for the calendar period. So what we've done so far, today we've introduced the Cox proportional hazards regression model. We've discussed how it is very similar to Poisson. Both the models make a proportional hazards assumption that we can actually test by fitting time by covariate interactions, and we can also investigate the proportional hazards assumption by using scaled Schoenfeld residuals. The main difference between Poisson regression and Cox is that the Poisson regression explicitly models for the baseline, assuming it's either piecewise, whether it's either constant or piecewise constant over time, while the Cox model allows the hazard to vary freely over time. And we can make the Poisson regression more Cox-like by making the time pieces smaller and smaller and smaller. The hazard ratios from a Cox model are automatically adjusted for confounding by the underlying time scale, and that one should choose an appropriate time scale. The key exercise for today is exercise 9 on localized melanoma modeling cause specific mortality using Cox regression, and this will be compared with exercise 7, where we did much the same thing for Poisson. We also exercise 10 is examining examining proportional hazards, and then we do some Cox regression for all-cause mortality, Cox for cause specific, and then we also investigate using the diet data. References are there. So thank you very much.